Hey guys, and welcome back to another AP Physics C video. Today we're going to be doing the rotational inertia of a uniform rod about its center. So last time we did about its end. This time we're not going to do about its end, we're going to do about its center. So we're going to assume that this rod has uniform density, length L, and mass M. So here's what we're going to do. Like last time, we're going to visualize a little dx, or a little dm that has a little dx that is x away from the origin, right? So just like last time, we're going to say rotational inertia is equal to the integral r squared dm. But we know in this situation, our r, which is how far away you are from the axis of rotation, is your x. And I know I want to put that there. So this becomes x squared dm. But just like last time, since I have uniform density, I'll come over here and say lambda, which is the linear mass density of the rod, is mass divided by length, which is also equal to dm dx. Because now you might be thinking, why didn't I say dl? Well, I'm not saying dl because my coordinate system is dx, right? It's the same thing. If I do this, if I sum up dx from 0 to l, it'll give me l, right? That'll give me the length because I'm just summing up all the little dx's and dl's. Well, a better way, I'll show later about the integration bounds. But if you think something's wrong with those integration bounds, you're probably right. Just don't worry about it. So what we're going to do here is we're going to transform this to find dm. So we're going to say m divided by L, or we'll just say lambda times dx is equal to dm. So now I'm going to take this integral. I'm going to take this integral and sub in everything I was just given. So now I have this integral. And you might be thinking, well, now you don't have integration bounds. Are we not going to get an indefinite integral? We're not, because I'm about to put the integration bounds in. I was saving them best for last. So now you might be thinking, well, what's our integration bounds? Well, let's think. If this is a uniform rod and it's about its center, well, what is this point right here? And if you said it's L over 2, you're right. Because now if I take the length and I divide it by 2, well, that's how long these segments will be. So this is L over 2, as is this segment L over 2. But at this point, that is negative L over 2. That's how far away from the origin we are. So if you could guess, the integration bounds will be from negative L over 2 to L over 2. So now I'll just, like last time, pull out my constants. And this is what separates us from the integral last time, the integration bounds, because otherwise it looks pretty similar. And we'll get lambda, and this integral becomes x to the third divided by 3 from negative L over 2 to L over 2. And this becomes lambda L to the third over, okay, now what's 1/2 squared? Well, what's L over 2 squared? Sorry, to the third. It's L to the third divided by 8, because 2 to the third is 8, and 1/2 to the third is 1 over 2 to the third. Sorry, is 1 over 2 to the third, which is, this is what I mean. 1 over 2 to the third is 1 to the third, 2 to the third, giving me 1 over 8. Bam, done. But there was also that little divided by 3 that I'm forgetting about, so I'll have to put that there. And now minus, and the other one is going to be negative L over 2 to the third, which will become negative L to the third over 8 over 3. And I'll just clean this up a bit. Lambda L to the third divided by 24 plus L to the third divided by, that looks like E, L to the third divided by 24, because negative negative makes a positive, and now this becomes lambda 2L to the third divided by 24. I'll simplify that fraction. Oops, simplify that fraction. And it becomes L to the third divided by 12. And now I'll sub in for lambda, so I'll get m over L is equal to, times L to the third over 12. And this will become 1/12 ml squared. And if you recognize that, that's because this is the correct derived equation for rotational inertia about its center. And yeah, that's pretty much it. That's all you need to know for that derivation. Hopefully this helped you guys, and yeah, I'll see you guys in the next video.